Okay, then let's continue. And the last thing that I would like to do is to show you some pictures essentially, and make a little bit the point that once you know this, so what you now know is how to convolve. Oops. Yeah. Huh? Yeah, you see it. That also still works. Oh, it stops my recording, does it? No, there it is. I saw it. Sorry. There we go. So once you know all of this, so once you know what a convolution is, so you know what this means, which we now discussed, you know that's an H, you know what the hemodynamic response function is, then in principle you can go and simulate the predictions based on your experimental paradigm. And I also strongly encourage you to do that before doing your GLM analysis, to actually have a look, especially if you're trying things like, for example, not using just stick functions, but boxcar functions, or use parametric regressors, to have a look what this actually predicts in terms of your HRF in your regressor or your regressive function. So the reason I opened MATLAB is that when I worked on this stuff, I isolated a lot of the SPM code from SPM. So usually when you use SPM, you basically use it as a black box and it just does everything, and it's not that easy to track what it's actually doing, because there's also no documentation of that. But so in the code that comes with PMFN 27, buy it now for only $10. There also comes code that does these basic things of the GLM based on the SPM stuff. So, for example, here you have what we just discussed, so that you have the difference of two gamma PDFs that are computed by SPM. There's also code that creates these regressors, and this is actually where I want to continue in a second. The convolution itself, so you are hard pressed to find where SPM does the convolution, because it does the convolution as a first order Volterra integration or zero order, don't know right now, but this is where the convolution happens. So what I'm trying to say is, if you do your own GLM analysis and you really want to understand how SPM creates your design matrix, or FSL creates your design matrix, have a look at this code and simulate the stuff. So we use that in Lilla's project. We actually use that a lot, so to have a look, because the SPM output only shows you your design matrix, and then you can try to look at it and from the gray values infer what you actually now have modeled, but one can do more. So I used this code to do some, if you want, simulations here. So the first thing that is of interest with respect, let's see where, can one zoom here? No, it's not better. No, let's do like this. So the first thing that is of interest with respect to the generation of design matrix regressors is that the convolution in SPM actually happens at what is called micro-time resolution. So the onset that you specify, so for example you say at 7.3 seconds after the run start there was an event, and at 10.6 seconds and so on. This is represented by stick functions at a quite high temporal resolution. I think that's usually 1 TR divided by 32, I think. So 32 time points per TR, which is of course not the sampling rate of your data acquisition, which is of course still TR. But this is where the onsets are registered, and then also the convolution with the hemodynamic response function is done. So this is what you see here with these blue dots. So this red is the stimulus onset function. Here there are a lot of zeros of the stimulus onset function, and the blue dots are then the discrete outcomes of the discrete convolution of the onset function with the hemodynamic response function. And this is then subsampled or sampled at the time of the TR, and then usually at the time point that is in the middle of the TR. So that's this 32 and 16 parameters that you always find in SPM. So you have, I think, 32 bins per TR, and then the middle point, so roughly 16, is chosen as the one that you actually put into the design matrix. So the subsampling here are the black dots. So this of course makes sense because with the hemodynamic response function you can have infinitely high temporal resolution, so you can be very precise with respect to the timing. If you would do the whole thing only at the level of the TR, then of course if you would have a quite long TR, like in the old days 2 or 3 seconds, then this would be a very unsophisticated prediction. But this is something that's kind of an additional level of complexity that happens in the convolution step. So that's convolution at the micro time and then subsampled for the design matrix regressor. That's a more technical thing. The question then is what qualitatively happens, and this is something one could study also analytically. So I always invite everyone to do a master thesis on this, so to study analytically how this canonical hemodynamic response function convolution business relates to the intuition of stimulus onset functions. So analytically, that would be to show analytically, so mathematically, that things like this, which I will explain in a second, happen. The other way you can of course always do things is to just do it and look at it. So this here is an example what happens if you use different kind of what is called event durations or boxcar functions. So instead of having only a stick, you can of course, and this is what convolution allows you, put in any input sequence. So that we are only always looking at stick input functions is just because I don't know. One can of course put in also continuous input functions. So for example, something that you get from the EEG, if you look for example at the alpha power over time, you can put this as a continuous input sequence and then get a bold regressor for that, or whatever. What some people always discuss is that especially if you have events that extend over time, so for example in decision making where people take like 12 to 15 seconds to do a certain decision, you can extend the predicted response in time, and this is what's shown here. So for example here the regressor, so the stimulus onset function, which I should replace by event onset function, is going up and then it's staying at 1 for some time and then it's going down again. And this blue thing is the predicted response that you get in response. So for stick you get 1 bump and then that's it. If you keep it up for a little bit longer, the whole thing gets longer, but it still doesn't extend longer in time. If you then extend it in time, then at one point it levels off and stays at that. But for example, what is analytically interesting here is the question of when does the scaling turn into leveling off, which one can compute. So if one looks at this is I think 1 or 2 length of the kernel. I don't know. I mean, one would have to mathematically look at that. That's interesting, and then one would have kind of the knowledge what actually happens in this model. but I don't find that in the literature. So that's one thing. So if you extend the duration of an event, and these events always have the same height. Now doing this. Wait. Another thing that is quite popular is to use parametric regressors. Again, this would be stick functions, but now with a varying height. So here you have a stick function that is a little bit larger in height, and here a little bit lower, here also a little bit lower, and you see that the response is then scaled appropriately. Also then if you have a negative one, you get a negative prediction, which you may or may not like. Both of these simulations are in the scenario when the events are really sparse in time. So you see that something is happening here, and then the next event only starts quite a long time, so definitely longer than one kernel length. So one, by kernel I mean the hemodynamic response function. So one hemodynamic response function with later. Of course, it's more interesting what happens if you put things closer together in time, and this is what this last simulation shows, that so here you have them spaced appropriately. Here they get closer together, so you see some merging here of the posthumous undershoot with the beginning of the next hemodynamic response, which you also see here. So you see a little bit of a decay in the peak if things go closer together in time, and at one point things start to merge even more, so that in the end you get to something that looks essentially in this case like this. But if you look closely, of course, here you have some peaks, so some events that are close together in time, and the response looks like this. Here you have one thing that is essentially the same as many peaks, but continuous, and the hemodynamic response function is only as high as the stimulus onset function, where here it's a lot higher. So again, these are kind of analytical features that would be interesting to explore, and then basically state in theorem form and proof, and then it's clearer what's actually happening with this model. But until some master student finally does that, you all have the possibility to simulate your GLM, specifically if you are not quite sure whether you should use this extended thing or you don't want to use, or even just to communicate clearly what the effects are that you want to predict in, or how you predict your effects in some fMRI analysis. And you now have the code for it, because this stuff is all done in this function. Of course, you still would have to work yourself into it, and he's the guy who did it all. Questions about this part? No. Good. Then this is essentially what I wanted to say about this step of going from a stimulus onset function to one regressor in the design matrix. So this is what we now discussed for the first sessions of this year, and based on this we now have, if you look at it from the top, we have one regressor in our design matrix, which has always these peaks here, and then they go away, and another peak, and then they go away. So this is one column in the design matrix. So we have one column by now. Of course, a design matrix usually has more than one column, and the next thing that we now want to look at is first something, a little bit of nomenclature that can help us to talk about multiple regressors in the design matrix, and a little bit some terminology and concepts to discuss maybe how good these kind of different design matrices are, and then to discuss as one or two, maybe only one specific form of design matrix. So right now I'm always thinking about, you have a couple of conditions and you show them and you create these design matrices. And this is a typical thing to do, to use this, but one can also use it a little bit differently in this PPI business, which will then be the thing after what we do next. Yeah. So basically we now go from first level regressors, which we discussed now, we go to first level design matrices. So to look at multiple regressors. Yeah, so that's the conceptual shift that we do now. And of course, in the handout or book, we now go to chapter 28, first level design matrices. Yeah, everybody happy? Good. So, first level design matrices. And in terms of discussing general design matrices for fMRI, the first two things, or the two things that I actually want to do, are to talk about I just write it out. It's a little bit long. Linearly independent orthogonal and uncorrelated regressors. The thing is, as soon as you go into some discussion by fMRI researchers how to do an experiment, the question is, when should you present your stimuli? As soon as you do that, there will be people who say, oh, your regressors are correlated. Is this orthogonal? It needs to be regressors correlated orthogonal. And it's completely confusing what anyone means by these things. Usually they can also not really tell you what they mean by this. So it's helpful to discuss what these terms mean in some detail, and also particularly emphasize that they don't all mean the same thing. And then the second thing, which we will do then starting next time, is measuring design efficiency, which for a long time was what people referred to when they talked about power in fMRI. So I guess you have some intuitive notion of what power means from undergrad statistics, although my intuition from undergrad statistics and power was only that something like power, so that's good, power is good, but it was not really clear what that really is. To give some notion of design efficiency, or we will actually not use the word power, but it's what now, for example, Jörg Dürnes and Lars Poldrack and so on, they refer to on their website where they do power analysis. I think the first level power or whatever. For some time, this was really what people really worried about. So how should I put my stimuli in time? Nowadays, when people talk about power in fMRI, they mean what everybody meant with power all the time is, so how many subjects do you have, essentially. So these are the two topics. And we start with the first one. So the question, the regressor dependencies, maybe. So the question is, let's say I have 3 conditions, and I want to, my 3 conditions, I want to present, let's say, 10 times to a participant during a single run. When should I present them? What is a good idea? So not necessarily about the order, but so whether I start with condition 1 or condition 2, but how should I space them in time, essentially? And if you look at that from a design matrix perspective, and you have your 3 conditions, then of course the question is, if here is time 0 and here is the end of the run, time t, you can do something like this. You can present condition 1 in the beginning, and then sometime later you do condition 2, sometime later you do condition 3, and then you do condition 2 again, maybe then you do condition 2 again, and then you do condition 1, and you do condition 3. So it's this kind of spacing of onsets that is of interest, and this can be done not so ideal if you, for example, present multiple conditions at the same time. So, for example, if you choose to present at time 0 condition 1, condition 2, and condition 3 at the same time, and you want to look at isolated effects of condition 1, condition 2, and condition 3, then of course you expose the participant to a mixture of these inputs, and you should always keep in mind that you only get a single number for each time point that you measure. So that means that if you present all conditions at the same time, what you observe is a mixture of this. Now, I'm not saying that this is necessarily a bad thing. So one can also do interesting things by sometimes showing things together and sometimes then isolate things to look at interactions and so on. But it then depends on what happens at other times. So yeah, essentially the question is there a language to describe how these kind of things are related? And one thing that is clear just from the mathematics of design matrices is that if a design matrix is if you have regressors or columns in the design matrix that are completely identical, then you cannot invert this matrix, and the evaluation of your design, so the estimation of your model, will just fail. However, the thing is, it's not the case that in general so this is a very specific case. In general, there will be dependencies, so linear dependence, non-orthogonality, or correlation between regressors. In general, this is not so bad, but it's only if it's too much, then at one point the whole thing doesn't work anymore. Yeah. So I'm not now trying to explain you how you always get completely linear independent, orthogonal and uncorrelated regressors. I'm just trying to give you a language to describe dependencies between regressors, and be aware that different dependencies mean different things, and then in a way also just make you aware of that, and give you some language to discuss it and argue that your design is a good design or not a good design. Yeah. And the important notions that we need to discuss is before we can go any further with this intuition, are these notions of linear independence, orthogonality, and uncorrelatedness. Yeah? And this is what I want to do now. So a design matrix, as you remember, is a matrix that has, for the GLM, has n rows and p columns, p being the number of regressors. And of course, to estimate the beta parameter, what you need to be able to invert, maybe I didn't say that clearly enough before, is this product of the design matrix with itself, and to be able to compute the beta parameters. We will also later see that, and maybe we've seen that also previously actually, that the variance of these beta parameters also depends on the design matrix, and being able to quantify dependencies between regressors in the design matrix also helps in this regard. So what we are now looking at is a design matrix being composed of multiple vectors. X1 to xp. What I mean by these are just the columns of the design matrix that from papers and from what I've drawn previously look a little bit like these Western blots in molecular biology. But of course have nothing to do with that at all. So these are just the columns of the design matrix, and for example x1 is then just a vector with entries like this. Yeah, so this is what I'm talking about right now. So we have these vectors and they are n-dimensional vectors. Yeah? So lists of n numbers. These are the regressors that we just generated based on convolution and subsampling our microtime resolution. Yeah, so this thing in where you remember these black sticks. These are the ones that I now talk about. And to talk about the relationship between different regressors, it's helpful to focus on two regressors. So we start with two regressors, x1 and x2, and we assume that they are n-dimensional, meaning they have n entries. Everybody happy with what we're talking about? So just a column of the design matrix, two columns of the design matrix. Now there's a very nice paper which I'm using as the basis for this, which is in the bibliographic remarks of this section. It's a paper from 1984, so it's a really old paper. Not really old, but it's not so old. It's a little bit old. It's not that young anymore, but still quite good looking. So meaning that this has been discussed for quite some time, and that there's no reason that in cognitive neuroscience we should be confused about this. So and on this paper, which I don't remember the author, I'm discussing these things. Does anyone have my notes there? What's the paper? Rogers or something like that? Rogers, 1984? Or? Yeah. Good. It's a good paper. So it's really short. It's 2 pages or so. So I really recommend reading it. He has also, I think it's a he, also has a couple of other papers which are really like tutorial, basic tutorial papers for GLM analysis. In an applied setting, because you can have these mathematical things about GLMs which sometimes are not that interesting, but here's quite some applied things. Now, based on this paper, Rogers 84, and of course general knowledge, we can define linear independence. This is of course the same definition as in linear algebra. Linear independence. So two vectors x1 and x2 are linear independent x1 and x2 are linearly independent. If there exists no A element R such that A x1 equals x2 for x1 not being x2. We will go over examples to make this more concrete, but what this means quite straightforward is if you have some vector x1 and you compute its scalar product with a scalar, and then you get the vector x2, then they are linear dependent. Yeah. So for example, if you have a vector 1, 1, 0 and you multiply this by 2, then you have the vector 2, 2, 0, and here there exists an A, namely 2, to multiply x1 to get x2, then they are linearly dependent. Yeah. If there exists no A like this, then they are linear independent. We will compare this. So first appreciate that I'm just giving you the definitions, and then we will go back and talk about the definitions more and do examples. Orthogonality. So two regressors are orthogonal, or two vectors x1 and x2 are orthogonal if the dot product, so the scalar product, which we luckily talked about last time in the other course, is 0. Yeah. So the typical intuition for that is that the two vectors are at a 90-degree angle. So for example, if you think in R2, so in a two-dimensional setting, and you have the vector 0, 1 and 1, 0, which you can visualize if you want like this in R2. If you compute the scalar product, you get 0, 1 times 1, 0, and this is 0 times 1 plus 1 times 0, which is 0. So they are orthogonal. That's what orthogonality means. And uncorrelatedness is of course related to correlatedness. Two vectors are uncorrelated. So x1, x2 are uncorrelated. If the dot product of the centered versions of the two vectors is 0. Where x1 or xi, so this one with the bar, is the average value of the respective sorry, that gets a little messy here. So the bar is 1 over n sum so the arithmetic mean, and this 1n is a vector of n ones. So that this is well defined. So you have a vector minus the scalar product of a vector of ones, and then you form, then you transpose it, and then you multiply with, in the dot product sense, with the same thing here. maybe before I go on with that, so the notions of linear independence and orthogonality, they are proper things to apply to vectors. If you have a linear algebra background, so you know that there are vector spaces where things can be linear dependent and can be orthogonal. Correlatedness actually is not really a term that applies to vectors in a too meaningful sense, unless one defines it like this, because correlation usually is used in a probabilistic setting. Of course, you know things like the correlation coefficient, and then you can compute the correlation coefficients of random variables. Yeah. So talking about correlated regressors is it's a little bit, one can do it and one can define it like this, but one should then be careful that one doesn't mean by talking about that two regressors are correlated that one necessarily means that the regressors are realizations of random variables, because often that's not the case. If you design an experiment and you say condition 2 happens at 10 seconds, then either you model yourself as a random number generator, then this is a random number, or you just, and specifically in the setting of the GLN, you just define it. So the design matrix entries in the GLM setting, so in our probability distribution over the data, the design matrix is the last thing in this setting that actually assumes some notion of randomness. If you go to Bayesian settings, then you might have a probability distribution over beta and over sigma square. But over the X, you can also define a probability distribution if you want, but then you are immediately in some different setting and not in the GLM setting anymore. That wouldn't be called GLM anymore. Yeah, so this is why talking about correlatedness of regressors is, if one defines it like that, so it's fine, but be careful to, that you don't confuse this kind of a category error. Correlatedness is something that applies in principle to random things. Good. Yeah, if of course, if the mean of so the average of x1 and x2 is 0, and then of course uncorrelated two uncorrelated regressors or two uncorrelated regressors are always orthogonal, because then it's the same. So if this part is 0, then it's the same with orthogonality, but it doesn't need to be. And the point of this whole thing of defining these three terms is then, of course, to look at some cases and study that it's not necessarily the case that things that are orthogonal are also uncorrelated, or that things that are uncorrelated are also orthogonal. So this is often, people just say, it's uncorrelated, so this is orthogonal, yeah, it's orthogonal, and it's, one can look closer. And this is what I try here by means of example, very much, it's not copy and paste because I think the examples are different, but it's very close to the Rogers paper. So so the first example is an example of two vectors x1, x2, which are linearly independent. So they will allow us to do estimation of the GLM if we would specify it, because only if the design matrix is really degenerate and you have complete linear dependence between two regressors, then you cannot estimate it. If it's not the case, if it's not linear dependent, then you can invert it. Maybe sometimes better than in other cases, but definitely, so this would be proper regressors for something, for your design, not for something, but for your design. but they are not orthogonal and not uncorrelated. Yeah, so meaning these is an example for two regressors which are correlated and which are not orthogonal, but which are linear independent and hence still work for model estimation, for inverting it. So the example goes as follows. It's just 4 entries. So x1 is this, x2 is this. So linear independence is always a little bit hard, or it's kind of these two criteria. It's in a way the most tricky one, because to check whether they are orthogonal or correlated, you just have to compute something, and then you know it's either 0, then things are orthogonal, or uncorrelated. But for linear independence, you need to prove that of all possible choices for A, and A is a real number, this thing does not happen. Yeah, so A is a real number. So in principle, we would have to test all real numbers to check whether somehow we can transform x1, or in this case x2, into x1. Here it's relatively straightforward to see, because we are only allowed to do a scalar multiplication. And when we do a scalar multiplication and multiply 1 by some scalar, we always get the same result. Yeah? So if we multiply 1 by A being 4.2, then we get 4.2. If we do this again, we get 4.2. So the first 2 entries of when we would be able to do that, actually I'm doing it the other way around here, so don't get confused. So like this. The first 2 entries of x2 always need to be the same if we do this. And here you see that x2 has 2 first entries, 2 and 3, which are not identical. So there cannot be an A that transforms x1 into x2. So x1 and x2 must be linear independent. Everybody happy? Good. But then if we compute the dot product, so x1, x2, that would be 1, 1, 2, 3, 2, 3, 4, 5. And that's actually also from this, you can already see that this is not 0, because there's only positive things that get added. And then you have 2 plus 3, that's 5, plus 8, that's 13, plus 15, that's 28, I think. So that's not 0, so they are not orthogonal. And then I also computed the correlation in our definition here. And what I get for this is 3.5 by some magic. So of course you would first have to compute the average and then subtract the average and then compute the dot product, and then you see that this is not uncorrelated, so correlated. Meaning here that, or emphasizing that you can have regressors that still work for your GLM because they are not linear dependent, but they have a degree of correlation and they have a degree of orthogonality. Yeah. And in actually the next section, we will quantify that a little bit more. So basically, of course, the more correlation you have, the worse, in a way, not quite, but as a rule of thumb. but as long as things are not linear dependent, the whole framework of the GLM still works. Now, I think because we're hitting the 45 minutes mark, I think the next two examples, they are actually good homework. There are two examples of, so example 2 gives you an example of two vectors which are not, or which are linear independent. They are not orthogonal, but uncorrelated. And the last example is an example for a regressor where for the case of where the two regressors are linear, again are linear independent. And they are both orthogonal and uncorrelated. So so to familiarize yourself with these concepts, I strongly encourage you to compute and see for yourself that what I just written here is true. Maybe you also find some typo, then let me know. But yeah, so the point is that these notions, specifically orthogonality and uncorrelatedness, are not the same. So you can have either or. Crucial for the whole business of GLM estimation is linear independence. Yeah? So if somebody says, yeah, but your regressors are correlated, then you can say, yeah, they are a little bit correlated. We quantified the statistical efficiency like we did last time, but they are not linear dependent, so we can do the GLM. So don't let people confuse you with the correlatedness and with the correlatedness and orthogonality.
But like the aim is that your design of vectors would fulfill those three criteria.
Now the aim would be that you. The aim is hard to talk about, so we will next time discuss a measure of design efficiency and also look how this relates to orthogonality and uncorrelatedness. The thing is, this is only a mathematical criterion. So you can, and this is what we'll discuss next time a little bit more in detail, you can optimize your design so that it minimizes the variance of your beta parameters. Good. But that a design that you choose like this doesn't necessarily fulfill other criteria which you might also think are important. For example, that you have not psychological sequence effects, so that if you do this condition and then you do this condition. So in terms of the aim, if you do things in a quantitative manner, you always have to capture in some kind of loss function and then minimize the loss or maximize some gain function. And the question is always what you put in there. So you can of course say, okay, it's more important to myself that not to myself, but for the project or whatever, that I evoke sensible cognitive processes and observe a given behavior. And for this, I allow for some diminished statistical efficiency. So it always depends. So it's a little bit hard to say this is the goal. So currently, and specifically next time. So today was more about establishing some language. So next time we discuss how to optimize a design from a statistical point of view. And that's only the statistical point of view. Then there, of course, are papers where people not only thought about optimizing from a statistical point of view, but maybe also from a psychological point of view. There are other things that you need to take into account usually when you think about optimizing things, for example, how much it costs and risks that you expose people to and so on. So this is the long answer. Yeah. Okay, so then if there are no further questions at the moment, then let's stop here and next time talk about the statistical efficiency of event-related fMRI designs.